Okay, so hi everyone. So I think everyone here have really witnessed this rapid progress of machine learning in the last, 10 or 20 years, right? So we see so many different applications from small things like a small sensor to something larger and larger, even to a city, right? So today I'm not going to be here to talk about how amazing they are, but I'm going to talk about something that we realize that machine learning has a problem for. And the thing that I want to talk about today is one observation that if you look at this machine learning landscape, it really have a cost problem. Because building those things can be ridiculously expensive. So let's start from a very concrete example. So this is one paper that we have this year, where we try to build a recommendation model with 100 trillion parameters. Can anyone guess how much money do you need to spend to actually train such a model for one day? So we have multiple options. Who think it's like $400 per day? 4,000? 40,000? 400,000? Well, luckily it's not 400,000, okay? So this actually took us like $40,000 to actually train that model for one day. If you think about how expensive that is, it's like these two students take this very fancy car and just burn it in one day. So that's how expensive this whole thing is. And this is actually another example. So you all see this very big language model, right, GPT-3, can do a lot of amazing things. So the question that I kind of want everyone to think about is assuming we want to train a model that's 100 times smaller than the biggest GPT. And I'm not asking you to actually train the GPT model. 100 times smaller. How much am I going to spend? 500? 5,000? 50,000? $500,000? Oh, this actually is kind of cheaper than you thought. It only takes $5,000 to train something that's 100 times smaller than what people have today. And if you think about the amount of computation you need, it's actually running like 2.4 petaflops nonstop for 5 days. And just yesterday, there's actually a tweet get really viral yesterday. And some startups say, OK, it's amazing. We finally can train a model with 30 billion parameters with only $500,000. And everyone just jump in. Oh, my God, it's so cheap. If you have something like that, I think it's very easy to actually believe this thing is very expensive. And the cost of machine learning doesn't only come from computation and the storage, it also comes from the data part. So this is one thing that we are building together with one company in Zurich, where we try to consolidate all those environmental data to the single platform. So when building one of those applications, one thing that we need to do is to say, OK, there's a whole bunch of satellite images. We want to label how many trees are there. We give that to a human, and they try to label something like that. How much money do you think we need to spend to label one such image? $1? $5? $10? $100? Not $100. I would do that myself if it's $100 to label that, right? So this actually takes $10 to label this single image today. And we need to label 1 million of those. So if you put all of those together, I think I can convince you that building machine learning application today is ridiculously expensive. And the central hypothesis of my group is that if you look at the key bottlenecks today that really stopping machine learning to be applied to every single problem that we care about in our society, cost is one of such bottlenecks. And the research mission of my group is really try to bring down the cost. Not only bring down the cost for executing machine learning workload, but also bring down the cost of building machine learning applications. So where do all the costs come from? If you think about why this is such a hard problem to actually tackle, it's because the costs come from so many different angles. So there's a computation and storage cost. For many of those workloads, you simply require a huge amount of compute and storage to get the whole thing run. And then on the other side, there's the cost of the ownership of the infrastructure. With $1 on the cloud service provider, maybe you can only run that much flops per hour. If you combine this, that's how you get this ridiculous cost about training those models or hosting those models. But this is just about one model. If you think about the process of building machine learning applications, it's often an iterative process that you need to try a whole bunch of models. You need to have people's time. You need to have people to actually build those applications. You need to have the cost about your data, collecting annotation, cleaning your data, all those type of things. You need to have compliance to different regulations to make sure your system is fair and robust, so on and so forth. You also need to pay the operational cost, monitor your model, test your model, adapt, and scale. If you look at all of these angles together, it's actually a very hard problem to try to bring down the cost. So in my group, we work on essentially 2 questions. The first question is by looking at the cost of training such a model. We try to look at every single bit that you need to communicate through the network, every single floating point operation that you need to run, every synchronization barriers you are enforcing in that distributed system, every data movement and shuffling you are conducting, every piece of data you must hold inside your memory, and every single fast connection you are building between those machines to make those kind of infrastructure so expensive. And we try to ask, are all those things that is making training so expensive really necessary? If they are necessary, how can we adapt our infrastructure to make sure they are not, right? If they're not necessary, how can we design our algorithm to make them cheaper? On the other hand, we also look at the process of building machine learning applications. We look at the process of improving the quality of a machine learning model, continuous testing the quality of a machine learning model, and also adapt a machine learning model to different scenarios. How can we do those processes as systematic and data efficient as possible? So over the years, our project can actually summarize into these 2 umbrellas. On one hand, what we realize is that if you design this algorithm and the data ecosystem and hardware all together, you can actually significantly bring down the cost of training machine learning models. So we have done a whole bunch of theory about how to deal with compression, deal with decentralization, deal with asynchronization, and there's a whole bunch of systems that you can already play with. And on the other hand, what we also realize is that if you look at the process of building machine learning applications, many of those steps can be made very systematic. And there's a lot of things that you can save if you give your user more systematic guideline. So here we have been looking at this end-to-end process of building machine learning applications all the way from data injection to continuous integration and continuous quality optimization. So this is pretty much what we do. So today I'm going to take one very specific problem, and this like a red rectangle in the diagram, and try to show you a little bit about the concrete problem that we have been tackling. So, and technically, it's actually about how to jointly understand the reason about data quality and the machine learning quality together. If you have ever built a machine learning application by yourself, so you must have this feeling that building a machine learning application, at least getting some model, is not that hard. You can just go to your favorite cloud, you drag and drop your data into the system, you get a model, right? So that's what you are able to do today. So what we are curious about is actually what's next. Once you have this model, what if the model is not good enough? What can you do? And if you want to improve the model, what is the reason that this machine learning model is not doing well? And what is the most important thing that you can fix to make this model perform better? So this is actually a textbook diagram about what machine learning looks like, right? On one hand, you have your data. You pipe that through a machine learning training process, you get the machine learning model in the end. You can measure some utility of this model, right? You can say, yeah, so here's my validation accuracy, here's my fairness. This is the textbook diagram of machine learning. But this is not what happened in practice. In practice, machine learning never looks like this. Because often the case, you have a whole bunch of problems in your data. There could be missing value, there could be wrong value, and there are millions of those examples. If you look at machine learning in practice, and often the case, you have all those problems in your data. Traditionally, we cluster those data problems into these multiple dimensions: accuracy, completeness, timeliness, and consistency. And it's not that hard to see that those data problems can associate to some of this model quality problem. For example, if your data has low accuracy, maybe your model has low accuracy. If your data is not complete, you could be missing a significant subpopulation. You could have a model that's actually not fair. So this is actually one paper we had back in 2019. So we take a data set with a lot of missing value, a lot of wrong value, and we train a whole bunch of machine learning model on it. So as you can see, those different machine learning models, they do have different quality measure, right? Some of them are pretty bad, some are pretty good. But what actually surprised us is all of them actually stop at this magic number 76% F1. If you think about what that 70% really mean, this is actually what this data set can actually support. At this point, it doesn't really matter what machine learning model you are using. Your data set can only support this level of quality. And once you clean your data a little bit, right, you can actually take very simple classifier, and you have this 5-point jump in quality for free. So essentially from this example and a whole bunch of things that we see in practice, often the best way to improve your machine learning model is not to try a whole bunch of models, but to actually improve your data. But unfortunately, that's actually something that's very easy to say, but kind of very, very hard to do today. Because when users are trying to improve their data for machine learning, they are facing a whole bunch of challenges. First one, there are so many things you can do to improve your data. You can get more features, you can remove the outlier, get more data, clean your data, whole bunch of things. Given a data set, there are millions of possible ways you can manipulate your data to make them better. And users are often overwhelmed by what to do. And second struggle is not all of those things you can do on your data are equally important. Only a very small portion of it are actually useful. And then, after you fix your data, getting the feedback is actually very slow because you need to train a machine learning model to see whether the accuracy improves or not. If it doesn't improve, you try another thing. This feedback loop is actually very, very slow. And also make the problem even harder, real-world machine learning pipeline doesn't look like this. Real-world machine learning pipeline look like something like this. It's a program where only a very small component of the program is actually about machine learning, and the majority part of this program is about feature extraction, data transformation. If you put all these four struggles together, in our observation, many of the users are actually wasting their time and money fixing data problems that often do not really matter at all. But in the meantime, they are missing all those important ones. So they need help. So if you think about what the challenge users are facing, wouldn't that be nice if every single Jupyter notebook that you are using today have this magic button called debug? And once you click that, we highlight every single data operation you have that is causing fairness problem in your final machine learning model. And wouldn't that be nice if every single AutoML platform have this magic button called improve your data? And once you click that, you select the utility you want to improve, and magically we sort your training example from the most important one to the least important one in improving your model quality. So these are the two functionalities that we kind of hope to support for our user. But to actually make them happen, there are actually hard technical problems. So this is a technical problem that we hope to understand. On one hand, you have your data set, have a whole bunch of data problems, missing value, wrong value, a whole bunch of things. You pipe that through an end-to-end machine learning pipeline, all the way from feature extraction to machine learning training, you get a model. And then you can measure this machine learning model with a certain utility function. And what we want to do is try to derive this notion of importance on the data side. Which data example is most important for me to improve this model quality? And we also want to assign for every single data transformation operator an importance. To say, yeah, if my model have low utility, it is because of this operator. So this is the technical problem that we hope to tackle. If you think about this, there are actually three different sub-problems that are interesting. So first one, how can we define importance, right? So because we are trying to compress this very complex problem into a single dimensional number, how can we define what is a good importance matrix? And second, how can we compute it? And third one, how can we use them to do something useful? So let's go through them one by one. How to define importance? So let's assume we want to define the importance for this one of these four different tuples in your training set. So you have this red tuple. Let's say, yeah, what is the importance of this red tuple? I mean, there's something easy you can do. You can just compute this leave one out notion of importance. You can say, yeah, this is a whole data set. I compute the accuracy of the model trained on this whole data set, and then I remove this red tuple. You can already see this value already give you some very important signal about how important this red tuple is. But unfortunately, this is not enough for us. because it's well known that this value could be suboptimal. And it's not that hard for you to see why it is suboptimal. Just consider this very simple case that you have 2 examples that are bad, 2 examples that are good, and your utility function is formed in a way that as long as you have a bad example, you have very low accuracy. Only if you only have good examples, you have very high accuracy. And then if you do this exercise of leave one out and try to compute the value, it's very easy to see this bad tuple and this good tuple will always have value 0. Because this notion of importance do not really consider all those correlations between those examples, which often happen in practice. So what can we do? So one thing that you could do with a very solid theoretical background is actually consider all the combinations of tuples. And then for each of those possible subsets, you try to remove this red tuple, and then you try to aggregate all of them back together. So there are different ways you can aggregate those importance. You can just compute the average, which have a very close relationship with something called multilinear extension. And it's actually worked really well in practice in many cases. You can aggregate them in a certain way with different weights, then you get the Shapley value, right? Something have very sound game theoretical foundation, also works well in many practice. And then essentially if you think about these different ways of aggregating those values, there's actually a very interesting trade-off between how you weight all those like possible subsets. So this is actually one example. So assuming we get back to the example that we try to assign importance for every single data transformation operator in this program. So the x-axis is that I follow the importance from the most important one to the least important one, and every single time I look at one operator, I fix them. I fix them to the best possible alternative. So, and the y-axis is actually the improvement of accuracy that we have in this machine learning pipeline. So as you can see, right, so we only fix one thing, this leave one out notion of importance, yeah, performed really well. But once you fix more and more, you start to see this pretty significant gap between what you can achieve using uniform weighting or Shapley compared with leave one out notion of things. So it actually make a really big difference. Consider many, many of those possible improvements. But on the other hand, it also makes the computation super, super expensive. And that brings us to the second question. How can we actually compute those importance? It's actually pretty hard to do. So if you look at this end-to-end pipeline and think about how can we compute the importance by enumerating all the possible subsets of my data. And it's actually super, super hard. It's not something that I recommend you to do. So what we learned over the years is that you can actually do something to speed up this process pretty significantly. One thing that you can do is to actually approximate this pipeline into something simpler that we call proxy pipeline. You can approximate your noise model into a more independent notion. In database, we call that a cost table, right? And then you can approximate your feature extraction pipeline by just keeping the polynomials. Okay? In the database world, essentially you have this positive relational algebra query, right? You compile your machine learning pipeline into that. And then you try to approximate your classifier into something simpler, for example, k-nearest neighbor classifier. And once you take this view, you can actually compute those like Shapley value or those multilinear extension in polynomial time for this proxy pipeline and use them to debug your original pipeline. So it's actually pretty interesting. Essentially, given a program like this, you can take the feature extraction part and then try to track this data polynomials. Okay? So theoretically, essentially, every single feature extraction pipeline become a polynomial in the polynomial semi-ring. If you have this one-to-one mapping of the input and output of the pipeline, you have something like this. You can have a one-to-many. You can also do joins, right? And then you replace this machine learning part into something simpler, like a k-nearest neighbor classifier. And then you can actually compute things like a Shapley value in polynomial time, okay? Which are exponential in the most generic case. The complexity actually depends on the type of this pipeline, okay? On the shape of this pipeline. So once you take this view, you can get a pretty significant speed up. So essentially, if you do Monte Carlo on the original pipeline, compare with computing those values on those like proxy pipeline, so there are 5 orders of magnitude difference in how fast you can compute those values. And speed up is not the only thing. But once you have this proxy pipeline importance, you can also use them to do something useful. This is just one example. Assume you have a training set with a whole bunch of data problems. For example, here you see there are a lot of images with wrong label. And then you train a machine learning pipeline, and you'll say, okay, how can I identify those training examples with wrong label that really matters for my accuracy? Because then I can fix it. So the high-level idea is you can compute the sharpie value of those data examples, and then you can follow the importance from the smallest one to the biggest one, and then you fix them one by one. So here the x-axis is actually how many data that you fix. The y-axis is the accuracy of this end-to-end machine learning pipeline. So first one, if you fix your data in a random way, you can get improvement. Don't get me wrong. I mean, you are going to have a better model because your data is getting better. But on the other hand, if you follow this data importance computed on the proxy pipeline, you are able to save more than 3 times labeling effort, but achieve essentially the same accuracy. And accuracy is not the only objective. For example, here's another example where if you have the 100% clean data, it actually have some fairness issue. So in this case, if you randomly fix your data, yeah, on the accuracy side, you are going to pick on better. But on the other hand, if you measure the fairness of your model, it's also becoming more and more unfair. In this case, you can also put in this important calculation to say, okay, my utility function is actually fairness. Right? In this case, you are actually able to have something that actually give you 20% better accuracy compared with the completely dirty data, but in the on the other hand, give you still a fair solution in the end. So there are a lot of things you can do once you compute those importance in an efficient way. And this is something that you can already play with, right? So we have a product called Datascope. It's actually very easy to use. You can just say, yeah, so this is my machine learning pipeline written in scikit-learn. This is the utility that we want to optimize for, and with a single line of code, you can get all those importance on your data. And then you can do whatever you want with it. You can do data debugging, you can do explanation, you can do a whole bunch of things. So again, this is just a small component about what we are doing in trying to make building machine learning applications much more efficient. So there's a whole bunch of things that we could do. We could do theory on distributed learning. We could actually build the distributed learning system. We could actually try to look at every single component of how to understand the data quality problem for machine learning model problem. So again, we are very excited to actually work together, and if you are interested, we can have discussion offline, right? Yeah, so that's all I have for today, right? I'm now happy to answer whatever question you guys have. Yeah.